is something that we see everywhere. The majority of the information that we receive from our environment comes from the fact that it's coming, probably 80 to 90% of the information is coming from light sources. But what is light? Light has always intrigued man. The ancients used to think of light as a gift of the gods, and therefore it was immeasurable. No one could determine how fast it went, or where it came from, or what it was made of. It was a gift from the gods. But in the 1600s, Galileo began to explore the nature of light, and he was interested in finding out how fast light would travel. So he did an experiment using his telescope and the planets, thinking he might be able to get a way in which he could measure how fast light reflected from the planet back to the Earth. But because of the situation of not having developed technology, he wasn't able to determine the speed of light. In 1820, Olaf Remer, a Danish astronomer, actually did give a finite value to light by an experiment that he performed. And this was the first time that we actually found a speed for light that we could use to measure. And in 1920, an American scientist, Albert Michelson, did the most exact experiment up to this time to give us the value fairly of what we have today, which is 186,000 miles per second, or 3 times 10 to the 8th meters per second. Now what's that mean? That's a very fast speed. That means that if we could take a ride on a beam of light and we were allowed to bend it around the circumference of the Earth, we could go around the Earth 7+ times in a second. That's a pretty phenomenal speed. And when we come to measuring the distances to stars, because they are so far away, we don't talk about them in millions and trillions of miles. Rather, we use the speed of light and refer to them distance from the Earth to Alpha Centauri or wherever in terms of light years. Now, what is light? Again, scientists didn't know what light was. It wasn't until 1600s when Newton and majority of the people in the scientific community at that time believed light was made up of particles, just little billiard balls or tennis balls as they went away. And it wasn't until the 20th century that we started to get the definition of light under the quantum theory. And light was not just a particle, but it sometimes acted like a wave. And so now we accept the duality principle of light, where sometimes it acts like a particle, sometimes it acts like a wave. And this has grown into the theory that allows us to do many, many experiments that we never would have dreamed of before the quantum theory came. Now there are many kind of interactions that light has with substances. We can have substances which are luminous. In other words, they give off light by themselves. Example, a flame on a candle, an electric light. These substances, the sun for example, these substances give off light on their own. And the second kind of substances that we have are substances that are reflective. In other words, what they do is they give off light by reflecting the light back to our eyes from some luminous source. With relationship to substances, we can have substances where light can easily go through them, in which case they're called transparent. Substances which are somewhat cloudy or whatever, like you might see in a shower glass window or in an office building, these are called translucent substances. Or we can have substances which are opaque. They don't let light go through them at all. Now light can be reflected off materials, and that's the majority of the light that we receive for our information, is light coming from substances that reflect off others. Example, let's say we're at a lake, and the lake is perfectly smooth, no ripples in the water. And you look at it, and what do you see? Well, it acts like a mirror. We see the same thing from a mirror. Everything is just perfectly smooth and we can see images formed on the mirror. For substances that are perfectly smooth and react this way, they're known as specular reflectors. And how this acts is that if all the light were to come in parallel to the substance, then it would hit the substance surface and it would reflect off at the exact same angle as it came in, with all the beams being parallel. And in this case, this determined the laws of reflection. And the first one says that for every angle of the incoming beam that strikes a point on a surface, it will be reflected off at the same angle relative to an imaginary line straight down the center that bisects that angle, which is known as the normal. So the law of reflection says for every incoming angle, we will have an equal and opposite outgoing angle. And then if we look at it along a plane, we will see that the incoming beam, the normal, and the outgoing beam or reflected beam all lie on the same plane. And these two things become the laws of reflection. Now, we've all seen what happens when we look in a mirror. We see reflection, we see images. But what are images? Well, images are what are formed when we have the reflected beams of light intersecting. Not the actual beams of light, but the reflected beams of light. And we can use this principle for movie projectors, film projectors, all kinds of things. We can make reflecting telescopes because the images are formed when the light comes off the mirror and intersects, and that's the points where it intersects and makes an image. Now, there are other types of reflection. We can have reflection from plain flat mirrors, as we said, but we also, just as we said, can have images that are formed, but in order to do that, we have to curve the mirrors. And when we curve the mirrors, we can get images by causing the reflected beams of light to intersect outward. Another property of light is refraction. Refraction occurs when the beam of light goes from one density substance to another. For example, light goes from air into water. We've all looked into a swimming pool at some point, and we've looked down, and we've seen an object at the bottom of the pool, and what do you notice? Well, if you aren't standing exactly on 100% over it and looking directly down on it, you will notice that the beam of light coming back using that object seems to be nearer to you than it actually is. And it also appears to be magnified. And the reason why that happens is because when light goes from a less dense material into a more dense material, at the interface of the surface between the two, the light is actually broken. And the light beam will now go into the more dense material at a different angle. And it also will change its frequency and its wavelength. And it will shorten the wavelength. And that's why when you stand on the pool and you look down, the actual wavelengths in the pool are shorter, and that's why you think the object is higher than it actually is. And if you were to go down and try to reach for that object, it wouldn't be straight down from where you're looking, because the beam of light has now been refracted and bent down. There's another interesting property that has to do with refraction of light, and this was pretty much discovered and played with by Sir Isaac Newton in the 1600s. He took a glass prism, which is nothing but a triangular piece of glass, and he let sunlight come through it. Now, for all practical purposes, we think sunlight is white light. But when the light came through the prism, he noticed that it broke up into all the different colors of the rainbow. Roy G. Biv: red, orange, yellow, blue, indigo, and violet. And so he determined then that every particular color of light will have a different frequency and a different wavelength, and therefore has a different energy also. Then We also know that light, because of the property of refraction, if it goes the opposite direction, it goes from a more dense media to a less dense media. Let's say from a piece of plastic to the air. We put the beam in through the plastic to the air. The opposite effect is going to occur. The beam is going to leave to the less dense media and it's going to bend away. In other words, the angle in the less dense media is going to be greater than the more dense media. But we will come to a point as the angle inside the more dense media gets larger. There will be a point at the surface where the outside angle will be 90 degrees to the surface. And if you go beyond that incident angle, what happens is that the light will now no longer emerge into the less dense substance, but will actually go back into the more dense material, and the light is captured. And this is called total internal reflection. And if you've ever seen fiber optics lights or candles or some of those things, you'll notice that that's how it works. The light in the fiber optics can't get out. It only can get out at the end. So it's just bouncing back and forth inside those small fibers or cables. Another property of light is what we refer to as interference. Now, interference is a property of the wave-like structure of light, not the particle structure. And what happens if we can take a very small grating, a small piece of plastic, and we groove it with the very, very, very thin slits. Just scrape it so that there's lots of little lines in it. And now we allow light to go through it. What we find out is that the light will go through it, but because the slit is a little bit smaller than the size of the wavelength, what happens when the wavelength emerges from the other side of the groove, it's bent. And when it's bent, it will come out almost like a circle. But there are thousands of these little lines all the way through this grating. And each one of them, as the light goes through, will bend. And there will be places where these waves will overlap on one another. And someplace, the wave will constructively interfere, building up the amplitude and making it brighter. And there will be other places where maybe the downside or the trough of a wave will appear on the crest of the wave, which is the high part of the wave, and those two things will cancel out. And in those places, what you'll see is darkness. And those are the places where light is canceled out. And this is called an interference pattern. It has to do with the property of the wavelength again, and this is the property of polarization. Polarization occurs when we can filter out a single plane of light wave. Light usually comes out from substances in 360 degrees in all different directions. But if we were to take a polarizing filter, which is a particular film type of material, and it will select a single plane of emission. In other words, all the beams of light coming through here will be blocked except for one plane. And when it comes out in that one plane, the wave will continue in that direction, but will have no other directions with it. Now, if we take two of these planes and put them so they're parallel to each other, and both of them allow the plane to have the same orientation, when light comes through both of them, we put them together, light comes through both of them, they'll be able to get through. But if we do one simple thing, we simply turn the filter very slowly, and the angle now will allow the light to go through one filter, but only part of the light will go through the other filter. And when we're exactly 90 degrees away from each other in terms of filter orientation, no more light will come out. We use polarized filters many places. Particularly, a most common place is in sunglasses. And this will line up the light that's coming off the surface, which we call glare, and block it out.